Yo, I didn't expect so many people to sign on already. How's everyone doing? Can everyone see me? Can everyone hear me? That's the important part. I'm just making sure that everything is good on my end. How's everyone doing? I'm curious to hear how your Thursday's going. And it looks like maybe I think I'm going to be able to move the screen just a little bit more. Let's see. Looks a little weird on my phone, but I think we might be able to get a better view of everything. Not yet. Hold on. Let me move this a little bit. So if anyone registered for the live event, I know I said matrices, determinants, and Kramer's rule. We could do that if that's what everyone is down for, but I was thinking that today we were going to do summations. At the very end, I think this morning, I was covering those things with a student of mine, and I just got so into them that I feel like it's such an important skill to remember. So really up to you. Let me know in the chat if you prefer to do matrices, determinants, Kramer's rule, or if you want to do summations. I'm planning to do summations. If no one is fighting against that, then that's exactly what we'll do. Okay, I guess we're going to go with summations. Let me just go ahead and pull up my, there's a couple of things that I just got to fix up on my end real quick. Let me just go ahead and sign on with my iPad because I got to be able to write on the... All right, so it looks like it's going to be summations. The only person that voted today was Mr. Red. That's what we're doing. Awesome. Okay, so let's go ahead and get started. So what I mean by summations, the stuff that we're going to cover today, it's going to look a little bit like this. Whoops, that is a terrible sigma. We have this sigma here. N is equal to 1, and let's just pretend, we're going to do it to 20, and then we have the function 5, n plus 3. Okay, now what does this mean? This just means that you're adding this value, or you're adding the sums of the first 20 terms. So if I wanted to find the first term, all I would have to do is plug in 1 into the equation, the 5n plus 3, and that's going to give me 8. If I find the second term, that's going to give me 13. And if I continue the third term, that's going to give me 18, and so on and so on. And I need to find all the way to the 20th term. And I believe if I find that value out, that's going to be 103. Yes, speed on. I can't read the entire name, but you're absolutely right. The last term is going to be 103. But can you imagine if we were actually trying to add all these values every single time? No, we don't want to do that. So that's why we use a formula for something like this. So we're not going to do the convergence test. That's going to be a whole different thing for series. That's something I could do later on. But today we're just doing summation. Okay, so if we're going to go ahead and add these things, we got to recognize that this summation is an arithmetic. Why is it arithmetic? If you look at every single term here, we start with 8, and then we're adding 5 to the next term, and then we add 5 to the next term, and it continues on and on and on. Okay? I haven't done PDEs. I will do that soon. Because we're constantly adding, or if we're subtracting by something, then that would be an arithmetic sequence, okay? So if we're going to do an arithmetic, or in this case, it's going to be an arithmetic series, we have a specific formula for that, and that is this one right here. S of n is equal to n over 2, times a of 1 plus a of n. This is like one of the most basic summations here. So n is the number of terms. So whenever you see this, I just want everyone to keep in mind that this is the number of terms. A1 is the first term, and then a of n is going to be the last term. So luckily for us, we already know the first term here. We know the first term is 8. We know the last term is going to be 103. So all we're going to go ahead and do is use that summation. Let me write that in green up here. So our entire summation is going to be the n, which is 20 terms, over 2 times the first term, which is 8, plus 103. And yes, I think someone had already found out the answer to that. So if I just go ahead and use some PAMDAS in the parentheses, I'm going to get 103 plus 8, that's 111, and then times 20 over 2. That's going to be 1,110. That is the sum. So again, we completely avoided how to add all these values one by one, and all we did was use a summation for that. PDEs, I will do that sometime. Yes, this is only for a partial sum. Absolutely. Could you imagine, Adam? Adam said this is only for a partial sum. I just kind of want to talk about this. If we had the same thing here, and we had a summation, but they're asking us to find the sum of the infinitely many sums, or the infinitely many terms. So the first term plus the second, the third, the fourth, the fifth, on and on forever. This will actually diverge. This sum will be infinity. This doesn't equal a specific value. But today we're just going to focus on sums that do have a limit. So let's go ahead and try a new one here. I have a couple problems. Let's go ahead and start off with, let's continue using n. This is going to be 18, and then I have 5n minus 4. Okay, so as you recall, this is going to be arithmetic. You can go ahead and test it out, but for the most part, if you see this looks like a linear function. This is going to be an arithmetic function. So we need to find n, which is a number of terms, and in this case, it's going to be 18. A of 1 is our first term. All we have to do is plug in 1 into this function, and it looks like we get 1. And then the last term, which is 18, is going to be 5 times 18 minus 4. Tell me why I can't multiply 5 times 18 in my head. But I just want to make sure that I get everything here correct. This is going to be 86. And so now we're going to go ahead and find the sum. That's going to be the sum of the first 18 terms is 18 over 2 times the first term plus 86. And I'm just using a calculator, one, because I kind of want to be fast, and I don't want to make mistakes. Awesome. So 783. You can find the missing limits. Yeah, so speed is talking about a lot of things. This is kind of cool. With summations, you could really get into a lot of different methods and a lot of different types of summations. They're really fun, and they're extremely useful when you're studying calculus or any higher level math. All right, let's go ahead and write the next one. Let's talk about this function here. Let's go ahead and do 10, and then now we're going to have 4 1/2 to the power of n minus 1 here. Okay, can anyone tell me what this type of series or summation is? Is this arithmetic? Speed, yes. If you wanted to know, this is going to be a geometric series. And speed, if you wanted to know whether something is going to be divergent, you can try the integral test, which is what you're kind of doing. And if you get that the integral is equal to infinity, then the series is going to diverge. That's something that we will do later on, and that's going to be for Calc BC. Anyone that's studying that, that's what we can do later on. But yes, this is going to be geometric. Now, the summation for this, the formula is not like arithmetic. It is going to be a different value. It's going to be a different type of formula here. Now, this one is going to be, I saw someone put a over 1 minus r. That's not going to be the case. I'm going to show you. This is going to be a of 1 times 1 minus r to the n over 1 minus r. That's awesome. Learning Calc 1 through 3. Calc 1, 2, and 3 when you were 15. That's great. Okay, if anyone recognizes series, go ahead and tell me if this is going to be the correct formula for this. This is a formula for a geometric series where a of 1, once again, is the first term. R is going to be the common ratio, and n is still the number of terms that we're adding. So let's talk about a of 1. A of 1, we're going to go ahead and figure that out by plugging in 1 to our formula. And that's going to be 4 times 1/2 to the power of 1 minus 1. And that's just 4. Our common ratio is going to be 1/2. And the number of terms that we have is going to be just 10. Yes, college day memories. So here we go. If we're going to add the first 10 terms, we're going to go ahead and put 4 times 1 minus 1/2 to the power of 10 all over 1 minus 1/2. As you can tell, this is very tedious. I'm definitely going to use a calculator for this because there's no way that I want to calculate 1/2 to the power of 10. Turtle, this is the form. Ultimately, if it started at 0, if you wanted to find your first term, you would just plug in 0 to the equation. For today, I'm just going to either they're going to start at 1 or something else. Okay, so let me just go ahead and simplify this for us. You don't have to worry about doing all this work. A calculator can do that for us, which is really nice. And I get a sum of, 1,023 over 128. How in the world are we going to be able to do that by hand? There's absolutely no way we can do that. Okay. So this is geometric. Again, how do we recognize it's geometric? It's definitely not arithmetic. If you look at the equation, it doesn't look like a linear function. If you were to test all the points, or if you were to look at the first point, the second term, the third term, the fourth term, you will see that it doesn't add or subtract by something. It's actually being multiplied by 1/2 every single time. Okay, so let's go ahead and try the series here. Let's try a different one. Let's go ahead and do n is equal to 1 to 5 of 3 times 4 to the power of n minus 1. And we want to find this sum again. So we want to find the sum of the first 5 terms. And I'll put that equation up here again. A of 1 times 1 minus r to the power of n all over 1 minus r. Okay. Go ahead and tell me what you guys think my first term is going to be. I need to find that. What is my first term? My first term is going to be 3. Nice, nice. Thank you, chat. How do we get 3? We plugged in 1 into the equation there, and we got 3 times 4 to the power of 0, which is just going to be 3. We need the number of terms, which is going to be 5. And then we need our common ratio, which is going to be 4. Okay. And so we're just going to go ahead and plug that in to the S of 5 that I have written up here. So A of 1 is 3 times 1 minus the common ratio 4 to the power of 5 all over 1 minus 4. Again, you're more than welcome to use or to do this in your head or by hand. I'm just going to plug it into the calculator again, just because I don't want to get any wrong answers. I got 1,023 as my answer. Okay, check this out. I'm about to give you guys a curveball here. It's still going to be geometric, but you're going to see something's going to change. So pay attention to the way I'm about to draw this or write this out. Summation from n is equal to 10 to 31 of 3 times 1/2 to the power of n minus 1. Aha! So we want to find the summation of this. How many terms am I adding here? I started at 10 and I'm going to the 31st term. So I'm going from the 10th term to the 31st term. So I want to know how many values I'm actually adding. Because if I want to find the summation, I need to find my n, my first term of this series, and I need to find the common ratio. So can anyone tell me in the chat how many values we are actually adding? Because we started from the 10th term to the 31st term. And I'll give you a hint, it's not 21. Bobby said 22. That is 100% correct. Turtle, yes. So you got to be very careful when you're doing something like this. A lot of people like to just say, oh, well, you're starting from the 10th term to the 31st term. That means you're adding 21 terms. You're actually adding 22 terms. Every time we do this, I would suggest subtract the top value, or the upper limit, which is 31 minus 10, which is 21, and then add 1 to it. So the number of terms that we're going to have is going to be 22. Our first term is now the value that we get when we plug in 10 into the formula. So that's going to be 3 times 1/2 to the power of 10 minus 1. Looks a little big, so I'm just going to do 3 over 2 to the power of 9. This is why a calculator can really help us here. And then the common ratio is just going to be 1/2. So that stays the same. So if I wanted to find the sum, I'm actually finding the sum of the 22 terms between 10 and 31. Oh, Liam, this is like the foundation of calculus, the foundation of series. When you start learning a higher level math, this is exactly what you're going to see. I mean, if you're studying engineering, four-year series has summations. Everything has summations if you really think about it. So I think it's a very fundamental skill that we should be very aware of. All right, so let's go ahead and plug these values in. I have my first term, which is 3 over 2 to the power of 9 times 1 minus the common ratio, which is 1/2 to the power of 22 all over 1 minus 1/2. Yo, I don't even want to simplify this, but I'm going to for the chat. And as I'm doing this, keep in mind that these are recorded. They will be posted on my YouTube channel. So if you guys ever feel like you want to watch this or previous lives that we have done, I highly suggest that you do that. Okay, guys, here was my answer. Wow, it's a very small number. It became like 0.01171. It wouldn't even register it as a fraction, so we're just going to keep it like that. Okay, one of the things that I just wanted to throw out here is what happens when you change our parameters. So now it's from 10 to 31. Now let's talk about what happens when we did the arithmetic one. If we were taking the sum of infinitely many values, we knew that this was going to be infinity. However, what happens when you have something like this? Look at that. Now we're adding not the first 10 terms, not the first 20 terms, but infinitely many terms. So there's got to be a formula for this. Someone had said it in the chat recently, but I'm curious if they can go back and tell us what this summation is. We need to find a formula for this. This is what we call the infinite summation, or the infinite sum of a geometric series. Oh, yes. It's super important in stats. You know what? You're 100% correct. Especially when you learn like higher level stats and probability. I mean, they're extremely helpful. I mean, the standard deviation requires summation. We just don't see it much because it takes too long to calculate. Okay, let me go ahead and write the formula for the infinite sum of a geometric series. It is going to be a of 1 over 1 minus r. But there is one condition. Okay, the absolute value of r needs to be less than 1. A lot of people say, oh, if the common ratio is a fraction, then it's gonna have a sum, an infinite sum. That's not the case. It has to be the absolute value of it, and it has to be less than 1. Not just because it's a fraction, but it has to be less than 1. And once we have that, if we meet these conditions, now we know that the common ratio is less than 1, which it is in this case. We're going to be able to find the summation. And this one's actually pretty easy. The summation is going to be 3 over 1 minus 1/2. And now we can easily use some like basic complex fractions here. Multiply the top and the bottom by 2. 6 over 2 minus 1, or just 6. That is the sum. Okay, let me give you guys another one. So again, keep in mind, this is what happens when we're taking the infinite sum of geometric terms. So let's go ahead and write this one out. We have n of 1 to infinity of 4 times 1/5 to the power of n minus 1. Okay, so here we go again. Does this converge? Let's see. The common ratio, or the absolute value of the common ratio, which is going to be the absolute value of 1/5, does seem to be less than 1. So we know that this is going to converge, meaning that a solution is going to be is going to be found, and we're going to be able to use the formula. The infinite sum of a geometric series is a of 1 over 1 minus r, as I mentioned before. The first term is just going to be 4. So we're going to have 4 over 1 minus 1/5. We can multiply the top and the bottom by 5. And we get 20 over 5 minus 1, which is going to be just 5. That's how you find the sum. Okay, I see a lot of people that kind of left the live, maybe because summations are a little boring. Does anyone want to cover something else, or should we continue with some more summations? Because now I got summations with different powers. So I got some things for you guys. Up to you. Okay, let's go ahead and do, let's go ahead and try a different summation. I guess we can try one that we haven't done. So just keep in mind, we've done arithmetic, we've done geometric. Now let's go ahead and talk about what happens when you have something like to the power of 2. What I mean by that is what happens when you have a summation. And this is like, for example, to 15 of n squared. Yo, does anyone remember the formula for this? Whenever you have a summation, this is no longer arithmetic. This is no longer geometric. This is now going to be a summation that's squared. And this has a specific formula for it. So again, one of the things that is important to know is some of the formulas for these summations. And I have them here. Okay, I guess I should change this a little bit. Maybe instead of an n, I'm going to use a k. You're going to see why that's the case. So when you have something like this, whenever it's squared, we have to use this formula here. N times n plus 1 times 2n plus 1 all over 6. This is almost a little easier than the arithmetic or the geometric, because we don't even have to find the first term. All we care about is how many terms are being added here. That's the important part. Okay? So the n represents the number of terms that were being added here, and in this case, that's 15. So this entire summation is going to be 15 times 15 plus 1 times 2 times 15 plus 1 all over 6. You simplify this. Whoops, this becomes 15 times 16, and then we have 31 all over 6. Oh my gosh, how is that derived? You know what? That's a good question. I think that will be a, let me just simplify this. This is going to be 1,240. You know what? I'm actually curious how that is derived. I can do the arithmetic one. But one thing that you could do is you can say, or you can prove that this is going to be the sum using proof by induction. So we can definitely do that if the chat wants that. We can prove this by induction if we wanted to. Otherwise, I'm just going to continue going. But typically, I guess in high school or like whenever you're learning this in college, whenever they give you the proofs, you have to just show that this works by induction. But I'm just going to keep it like this for now. Unless the chat wants me to do proof by induction, I'm just going to move forward. But that's how you would do it. So here we go. Now let's combine everything that we've been learning so far. What if I have a summation that looks like this? Let's do 10. Whoops. Of 6k plus k squared. So now I'm beginning to have a summation, but now I have two different terms. Both of them have the variable k, so I definitely have to make sure that I am using the specific formulas. See you, turtle. Okay, so you notice how these two things are being added together? Luckily for us, we can go ahead and separate this, and that's exactly what we're going to do. We're going to make this 3k plus, we're going to make sure that we write each summation here. Yes, it is definitely a mix of arithmetic, and I guess you can say this is a quadratic or like a squared. So the first one is an arithmetic. How do we know that? I mean, it's just 3k, so you're constantly adding by 3 in every single term. So we're going to use the formula s of 10, or we're going to use this one, n over 2 times a of 1 plus a of n. That's for the first one. And in the second, that's the k squared. So that's the one where we have to use n times n plus 1 over 2n plus 1 over 6. Now, the first one is just arithmetic, okay? Pretty simple. We just have to figure out a couple things. We need to find n is the number of terms that we're adding. That's 10. A of 1 is the first term. So just imagine plugging in 1 into that value. That's just going to be 3. And then a of 10 is going to be the last term. So we're just going to go ahead and plug in 10 into that series, and that's just going to be 30. And then luckily for us, for the other one, n is just equal to 10. So we're just going to go ahead and plug that in. And now as we try to solve this, we're going to do 10 over 2 times the first term, which is 3, plus 30, plus, and then we'll take care of the other one. That's 10 plus 10 plus 1 times 2 times 10 plus 1 all over 6. And now we just got to simplify this. Hope that's still showing on the screen. It looks like it is, thankfully. And so this is going to become, again, I'm using the calculator just because I don't want to make any silly mistakes. So this is going to be 165 plus 385. Well, I guess I should maybe add that one. So 550 is going to be the correct answer. Okay, I don't think we have to factor them out. We could just separate them. And this is actually very useful whenever we're trying to show the limit definition for an integral. So that's something that we can talk about, and we can start including some limits in here and showing that what the integrals are equal to. Yes, definitely learning something like this in BC. Let me show you what they mentioned, or what they're talking about when it comes to BC. So if everyone remembers the formula for, let's just say we can do the right Riemann sum. It kind of looks like this. So k is equal to 1 to some value n. And then we have f of technically we do the b minus a over n times k times b minus a over n. So I don't even want to start on the first term. We're just going to go ahead and start. This is a right Riemann sum. Okay. Anyone in here taking calculus or below calculus? Let me know in the chat if you study or if you recognize this equation. This is the right Riemann sum for any area under the curve given the function. This isn't the trapezoid rule. This is just the right Riemann sum. So how does the left look like? That's a good question. So the left will look like this. Again, this is the right. So the left will typically have, like, you'll start at k is equal to 1. Or if some people will do k is equal to 2. But it will be f of, now but because we want the left, I'm sorry, is going to be b minus a over n times k minus 1. And then they'll just add the plus a. Everyone does it differently, but because we start at k is equal to 1, that's going to be our first, that's going to be the left Riemann sum. So this is the right, and this is the left. Now, as you can see, this is why we don't even use, or I don't like to use the left. I like to use the right to show the limit process of a definition. Math third, A plus, yeah, notice how you said A plus. That will be for the left, yes. So again, I didn't want to show, or I don't like to use the left particularly. I like to use the right side of this. But let's go ahead and I'm going to show you why this is kind of important here, okay? So we're going to leave this equation here, and we're going to try to show how we calculate this area. So the area, or the integral of x squared dx, and let's go ahead and use from 0 to, let's just say, 6. And that's going to be 72. So we are going to show, using our sigma notation, or the definition, or the right Riemann sums, why this is equal to 72. Okay. So let's check it out. You're right. I'm gonna try this equation here real quick. Okay. And we're gonna talk about why that's the case. I still think that it will be since I started from 0. Oh, I see why you did the A. You know, typically because I see what you're referring to. Okay, so let's just rewrite that real quick. So according to the right, I completely disregarded the A. In my head, I'm thinking that A is equal to 0. This will be our equation. K is equal to 1 to n of f of b minus a over n times k plus a. I believe polymath was saying a plus. And then we're going to multiply that by b minus a over n. Okay, so again, we are trying to prove the integral that's on top there. The integral from 0 to 6, and we're saying that this is going to be 72. So that's going to mean that our a value is going to be 0. Our b value is going to be 6, and we don't know how many rectangles we have, so that's why it is going to be n. So if we write our summation, it's going to look like this. F of 6 minus 0 over n times k plus, and in this case, the a is 0. Yeah, thank you, polymath. Times 6 minus 0 over n. So let's simplify this a little bit. So this is going to become 6 over n times k times 6 over n. Okay. So now let's go ahead and make some space in the blackboard. So again, don't forget that we're trying to prove that this is equal to 72. Let me go ahead and do that. Here we go. Okay, making this a little better, or continuing this, this is going to be f of, well, I guess now, since we know that the f is the x squared, this is going to become 6 over n k squared times 6 over n. Okay, now, one of the things to keep in mind is our summation. Well, let's first simplify it. So let's go ahead and distribute that squared. This is going to be the summation from k is equal to 1, and this is going to be 36 over n squared times k squared times 6 over n. All right. So one thing that I'm going to do is I'm going to multiply the 36 over n squared times the 6 over n. And that's going to give me this summation. 216 over n cubed times k squared. Now, as I make this smaller, keep in mind that our summation is really dependent on k, because that's the value that we're adding to our summation. So we're adding k is equal to 1, k is equal to 2, k is equal to 3, and so on. So then now what we're going to do, since the 216 over n cubed doesn't really matter at this point, just right now, I'm going to pull it outside. So I have 216 over n cubed, summation k is equal to 1 to n, and this is k squared. And if you guys remembered, we did this a couple of minutes ago. We talked about the summation of something like this, and we said that this was equal to n times n plus 1 times 2n plus 1 all over 6. So that's exactly what we're going to rewrite our summation down below as. This is going to be 216 over n cubed times n plus 1 times 2n plus 1 all over 6. All right, a few things that we're going to do is the 216 and the 6 can definitely cancel out. And that's going to leave us with 36 over n cubed times n plus 1 times 2n plus 1. And now I'm going to create some space in the blackboard. And as I'm doing that, keep in mind that because we're taking, now that we have this clear summation for the n values, we are trying to find what this area is. Now, this integral, the right Riemann sum, is the sum of all the areas of the rectangles underneath the curve. Now, we don't know how many rectangles we have, but if we have infinitely many rectangles, we're going to be able to find the exact area underneath the curve. So this is now going to become, or we're going to go ahead and take the limit as n approaches infinity, of 36n times n plus 1 times 2n plus 1 all over n cubed. Now, what does that limit equal to? It might look a little difficult to solve, but hopefully you guys can remember some of the rules here, that when the power of the top is equal to the power of the bottom, then this limit as n approaches infinity is just going to be the ratio of their leading coefficients. Well, luckily for us, we don't need to multiply this out. But what you can see is that if those two, or if these three terms were to be multiplied out, the leading coefficient for that is going to be 2n cubed. So then the leading coefficient of the top, or the leading coefficient for the top is going to become 72n cubed. Now we have 72n cubed on top, we have n cubed on the bottom. Therefore, the limit, because the degree of the top is the same as the bottom, is going to equal to the ratio of the leading coefficients. And this is going to equal to 72, which is exactly what the area from 0 to 6 of x squared dx was. And that's how we show, or that's how sometimes in calculus AB or calculus BC, you guys are being taught to find the the LRAM or the RRAM, and then you're taking the limit as n approaches infinity, and you're trying to show that this is in fact the integral from your specific parameters, 0 to 6 or whatever. Now we can try a different one and make it way more difficult if you guys wanted to. So let's go ahead and apply that. We're going to go ahead and use, I'm still going to use the LRAM. I don't like the R, I'm sorry, we're going to use the RRAM. I don't like the LRAM so much. So keep in mind that the RRAM is the summation from k is equal to 1 of f of a plus b minus a over n times k times b minus a over n. Thank you, Polymath, for correcting me on that one. It's a plus b minus a over n. And we're going to go ahead and use, or we're going to try to prove that the integral from 0, let's go ahead and actually use, no, let's continue using 0. 0 to 6 of x squared plus 3x is equal to, this is why we have our calculator, x squared plus 3x, this is going to be x. So we want to show that this is 126. Someone asked, how long did it take you to learn math to this extent, and any advice from someone who struggles? To be honest, I felt I was extremely good at math when I graduated high school. I took the AP exam. I got 5s on the AB and the BC. And then I got to college, and it really kicked me in the ass. So one of the things that I will suggest is just continue to practice as much as you can. One professor always advised to either watch videos on the same topic from different people or read different books on the same topic. And then slowly you start learning different techniques, different methods, and it slowly starts making sense. But honestly, if you're not practicing, if you're not putting in the work, and if you're not sitting down and try to, write problems down on your own, you're not going to get better. So that's my suggestion. Okay. So now that we're going to prove this, don't forget, a is equal to 0, b is equal to 6. Those are our parameters. We don't know what n is because it's actually going to approach infinity. So we're going to go ahead and plug that into our summation. So now we're going to have f of 0 plus 6 minus 0 over n k times 6 minus 0 over n. Now we're going to go ahead and simplify this. This is just b, or 6 over n, k times 6 over n. And now this is where things get a little tricky, because our f function is a little different now. Our f function, let me circle it in red, is this one over here. So we have to plug in the 6 over nk to both of these terms. So what this is going to become is 6 over nk squared plus 3 times 6 over nk. And then times 6 over n. Ooh, boy. Okay. Let's go ahead and simplify this a bit, and then I'll create some space on the blackboard. So now what this is going to become is 36k squared over n squared plus 18 over nk, and the whole thing is being multiplied by 6n. I'll definitely multiply that out in a second. But first, let me go ahead and create some space on the blackboard, as you guys already know. And by the way, if you wanted to review this or any other lives, they are pre-recorded. I post them on my YouTube. So if you have to go for whatever reason, you could always just look back. All right, let's go ahead and distribute that 6 over n. So now we have 216k squared over n squared plus can't believe I can't even multiply, or I don't want to be incorrect. So this is going to be 108k over n. Okay, so this is just two summations. So I'm going to go ahead and separate these two. Into these summations here. Okay, and now as you can see, again, as I mentioned, the summations are dependent on k, not n, because again, we're plugging in the 1, 2, 3, 4 into the value of k. We don't know what n is. So for each summation, I can go ahead and pull out these values. So now I have 216 over n squared, and then I have the summation k is equal to 1 to n of k squared, plus 108 over n, summation k is equal to 1 of n 2k. And now we utilize the rules for our summations. Let me just make this, I'll write our work here. So now we have 216 over n squared times, don't forget that the formula for k squared is this, n times n plus 1 times 2n plus 1 all over 6, and then plus 108 over n times, this is going to be the summation for just a arithmetic function, so that's just going to be n times n plus 1 all over 2. As always, I'm going to create some space here again. Let me go ahead and shrink this. It's like the work never ends, guys. Okay, I think that's small enough, I'm hoping. All right, back to these summations here, or these values. We can go ahead and simplify or divide the 216 by 6. So now we have 36 n times n plus 1 times 2n plus 1 all over n. That should have been an n cubed. Yes, it should have been an n cubed the whole time, because when I multiplied it by 6n squared. Whoopsie there. Okay, plus, and then now we have, this is going to be divide the 108 by the 2. And now we have 54n times n plus 1. And that also should have been an n squared. I can't believe I didn't multiply the n squared correctly when I distributed that 6 and at the end. So again, now what we want to do is we want to take the limit as n approaches infinity of these two values. Plus 54n times n plus 1 over n squared. That first limit we recognize, that's just 36. That's the one that we did last time. Or I'm sorry, not 36, that's 72. Plus this next one, if you notice again, the degree of the top is just the same as the degree of the bottom. So therefore, the limit is just the ratio of the leading coefficients, and that's just 54. And once again, if we add these together, we get 126, which was, from the very beginning, the limit of this function. Pretty neat. So sometimes that's exactly what they're going to have you do, especially if you're taking Calc BC for the first time. I know that they want to give you this extensive summation, and they want you to definitely try to find this. All right. Any suggestions that you guys want to cover? This is kind of fun. We kind of started with summations, and then we started leaning towards the RRAM and the LRAM, which was pretty fun. But I'm curious what else you guys would like to cover. Anything else in particular you wanted to review? Anything calculus-based? Is anyone covering a specific topic? We'll love to review that. These summations were just something that a student of mine was covering, so I thought it was kind of fun to look over. And then someone started relating it to the RAM, so that was fun. Triple integrals, partial derivatives. Okay. I'm curious how many people are familiar with these things. Taylor series, we can definitely do that. Okay. I think for the majority, so I'm curious who in the chat here is covering or is in Calc B3, or I say Calc B3, Calc 3. So we're talking partial derivatives, triple integrals. For the most part, I don't know if a lot of people are doing that. But Taylor series. Okay, yeah, partial derivatives. Yeah, if you're doing partial derivatives, you're for sure in Calc 3. How's that going for you? Oh, AP Calc BC. I just started Calc 3 this semester. Oh my God, partial derivatives next week. Oh, okay, so you guys are just in the beginning stages of that. Okay, so someone's in Calc BC. I see Calc 3. Someone's just starting partial derivatives. Let's kind of review. I completely agree that Calc 3 is much easier. Once you learn partial derivatives, I mean, once you do them, you're like, okay, this isn't that bad. Okay. Yeah, Calc 2 is kind of fun. Let's go ahead and just do some Taylor series, since that's kind of what everyone's going to be familiar with. Okay. So Taylor series, if you recall, which is actually pretty cool. I mean, I can't believe that these things were invented for us, and not even invented, but discovered for us to just start be able to create a Taylor series for almost any function. Okay, so if we're given a function, we can say that the Taylor series is going to be defined by n is equal to 1, or it actually starts at 0, whoops, to infinity, of f to the power of n, or not f to the power of n. This is the nth derivative evaluated at a specific value over n factorial times x minus a over n. And a is just where the function is centered at, so you can see it as like a translation. When a is equal to 0, we call that a Maclaurin series. Try with the absolute value function. Yo, come on. You're killing me here. One thing we would do, let's go ahead and try it. I think that the important ones that we should always know is, for example, like e to the x, and we can do sine and cosine, because that shows us the Euler identity, which is pretty cool. Yeah, so it's after series, because you should definitely know the notation here that you would do for series. So let's just kind of talk about an easy one, I would say. So let's just say I'm given the function f of x is equal to e to the x. This is one of the basic ones when they talk about Taylor series. But we're going to center this at a is equal to 0. That's going to make it a Maclaurin series, but I think that's kind of easier to digest for everyone. So the way it's going to work, okay, if you look at the formula, we have the nth derivative over n factorial times x minus a to the power of n. Okay, so sometimes they call this like find the first 4 derivatives. We can go further, obviously, but the idea is if you start off with a function, it's just the original, and then we're going to plug in f of a. And in this case, our a value is just 0, so we have f of 0, which is equal to e to the 0, which is going to be 1. I'm showing all the work here so that we can continue the pattern. Yes, this will turn it into a Maclaurin series. The Maclaurin series is centered at a is equal to 0. So now we're going to take the derivative, and that means that n is equal to 1. For the beginning one, it was the original function, so there's really no derivative. That's just n is equal to 0. The derivative of this is just e to the x, and then we have evaluated at a, which is the same thing evaluated at 0, e to the 0, which is just 1. If we take the second derivative, you'll see that's the same thing. So then the second derivative evaluated at a, which is the second derivative evaluated at 0, is just going to be 1. And then we're going to take the third derivative, which is e to the x, and you can see that the pattern just continues. The third derivative at 0 is just going to be 1. And so, again, you continue seeing that pattern once we have that. So now we can go ahead and create our Taylor series. Of course, this is called the Maclaurin series because it's centered at 0. but still technically it is a Taylor series. So the way it starts off is we take the first derivative evaluated at 0. So that's 1 over 0 factorial, because that's our end value, times x minus 0 to the 0 power. We'll simplify that. Just hold on. Plus the first derivative evaluated at 0. That's just 1 over 1 factorial times x minus 0 to the first. Plus the same thing, 1 over 2 factorial times x minus 0 to the power of 2. And that just continues. So if I simplify this just a little bit, this is going to become 1 plus x squared over 2 factorial. And if we continued, this will become this particular value. Whoops. Should be 4 factorial underneath. Let me make that a little nicer. So on and so on. This is technically, or this is technically the Taylor series, but it is the Maclaurin series for e to the x. Super important when we do that. Okay? Now, I want you to keep in mind, I want to have plenty of time. I want to do e to the x, then I want to do sine of x, and then I want to do cosine of x, because then I want to show you how Euler's identity is shown from this. So e to the x is just going to be that series. This is the Maclaurin series for e to the x. So just keep that one in mind, okay? I'll introduce it back again, but we're going to revisit that later on. So let's go ahead and erase our stuff here. And now we're going to do sine of x. And sine of x has a very interesting formula here, and it's very nice to find, and then to find a general formula for the Maclaurin series. But now instead of f of x being sine, we're going to do sine, or instead of being e to the x, we're going to do sine of x. And then a is equal to 0. Manuela, I try. I definitely try. Yes, I agree. Polymath, super useful. Actually, last night I was reading like the residue theorem, and I was doing some complex analysis, and a lot of the times, and it's still difficult for me to understand, but a lot of the times it will say, because the Taylor series of this is equal to that, then we can say that this is that, X, Y, Z, or it satisfies the specific condition. So obviously Taylor series and Maclaurin series, very, very important in a higher level math. Okay, so here we go. When n is equal to 0, the original function is just f of x, which is sine of x. And then at 0, now we know that a is equal to 0. This is going to be sine of 0, which is going to be 0. Okay, n is equal to 1. Let's go ahead and take that first derivative. That's cosine of x. So when you evaluate it at 0, that's going to be cosine of 0. That's going to be 1. Let's be careful here. Let's continue. Second derivative is negative sine of x. So that means that the second derivative evaluated at 0 is 0. And now we go to the third derivative. This is negative cosine of x. And if you plug in 0 into the third derivative, you're going to get negative cosine of 0, and that's negative 1. Okay, so we still haven't really found a pattern. It goes 0, 1, 0, negative 1. I'm hoping that the next one does in fact repeat, and that's actually going to be true. I wish I was as good as in physics as I thought I am, or as I think I am. I'm not the best. Maybe one day we can definitely talk about it, but I'm looking forward to discussing physics with you guys on the live. Let's go ahead and find the fourth derivative. Now, I'm just not even going to put like 4 parentheses. I'm just going to put a 4 so that you can see that this becomes negative sine of x. And then the fourth derivative at negative sine of x is going to be 0 there. Okay. I'm hoping if the next one is of 1, then we are good. We can continue. Wait, did I take I'm going to just double check that I took the derivatives right here. Negative sine and then the negative cosine. Oh, the next one, I'm sorry. This was positive sine. Important to do that. Otherwise, my series would not be correct. So now when we take the fifth derivative, this is going to be cosine of x. And now the fifth derivative of cosine of 0 is just going to be 1. So it does repeat. So it goes 0, 1, negative 1, 0, 1. And that's exactly what's going to happen. So let's go ahead and start writing our Maclaurin series for this. So we have original function at a, which is 0, over 0 factorial times x to the power of 0. That's fine. Don't even worry about that. And then now we have plus 1 over 1 factorial times x to the first, plus 0 over 2 factorial, x squared, minus 1 over 3 factorial, x cubed, plus 0 over 4 factorial, x to the fourth, plus 1 over 5 factorial, x to the fifth, and it goes on and on. So if you start noticing, all the values that have an even power cancel out. So we're really just left with these odd powers, and they're alternating. That's the beauty of this whole thing. So let me go ahead and make this smaller because I want to make sure that we write everything down. Okay, hopefully that fits. So then what we end up having is x, let me continue writing it in yellow. So we have x over 1 factorial minus x cubed over 3 factorial plus x to the fifth over 5 factorial. And if you trusted this process, this will become x to the 7th over 7 factorial plus x to the 9th over 9 factorial. So we can go ahead and this continues on and on. This is the Maclaurin series for sine, but we can definitely give it some type of formula, and it'll look like this. -1 to the, let's go ahead and do m plus 1 times x to the n over let's make it a 0. I'm sorry. Starting at 0, this will be -1 to the n of x to the 2m plus 1 over 2m plus 1 factorial. This is super useful, and if you recognize this, you'll be like, oh, this is always the Maclaurin series for sine. Okay? Now, we can do cosine. I'm not going to show you that because I definitely want to jump into the Euler identity, but just keep in mind that this is the Maclaurin series for sine. Now, what would happen if we had the cosine? If instead of f of x is equal to sine, f of x was equal to cosine. Well, I'm not going to show the work. That's something that maybe you could even try on your own, and I'm sure if you've taken calc, you know how to do that already, but I'm just going to shrink this a little bit, and I'm just going to show you what the Taylor series for, or Maclaurin series for cosine is going to be. So cosine actually starts off with 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the 6 over 6 factorial plus on and on. So basically what happens here is instead of the odds for sines, we're using the evens for cosines. So this is the Taylor series for cosine. I say Taylor series, but again, it's really a Maclaurin series because it's centered at 0. So now that we kind of understand that, let's go ahead and talk about the Euler identity. Okay, so let me go ahead and erase this, and I'm hoping that some people just have a good understanding of Taylor series and Maclaurin series and how to find that. But let me go ahead and erase some stuff. Actually, we'll just erase the whole thing. Okay, so let's talk about this. E to the I pi plus 1 is equal to 0. So let's talk about how we're going to get that, okay? First, let's go ahead and start off by writing the Maclaurin series for e to the x. E to the x, as we mentioned, is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial plus x to the fifth over 5 factorial. Let me go on just a little further because I'm definitely going to need some of these values. Okay. That's not bad, I would say. Okay, here we go. So let's just go ahead and start off first by putting I pi as my power. Now, what are we going to do? That means that for every value of x, we're going to go ahead and include an I pi. Or I guess for now, we could just completely disregard the pi. We can just do ix for now. Let's not worry about the pi just yet. Okay. So if we add that, this is going to be 1 plus ix squared over 2 factorial plus the next one. This is a third factorial plus the next one. I don't even know I'm going to have enough space for this. But we'll talk about what all this does. Okay, it looks like I could only make it up to the 6 factorial, but it continues. Okay, and then from here, we just have to utilize the idea of complex values. So for the first one, we have 1 plus I is just ix. Now that second one, we're going to square the I. But remember, this is a complex value, so I squared is negative 1. So this is going to become minus x squared over 2 factorial. The next one, I cubed, is negative I. So this is negative I x cubed over 3 factorial. And then the next one, I to the fourth, is just 1. So that's just plus x to the fourth over 4 factorial. And then it continues, plus I x to the fifth over 5 factorial, minus x to the 6th over 6 factorial, minus I x to the 7th over 7 factorial, and so on. So if you follow that pattern, that's exactly what you're going to get. And so now what we're going to do is first we're just going to group the ones that don't have any i's. So the ones that don't have any i's is 1, the x squared, the x to the fourth, the x to the 6th. So that's going to become 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the 6th over 6 factorial. Technically, I will continue that process, and now I can put plus x to the 8th plus 8 factorial, and so on. And then I'm going to go ahead and group the ones that have the I, and that's going to be all the ones that are left. Hopefully, you guys can kind of start seeing where I'm headed towards. Now, I'm going to pull out an I from everything. So I have an I and then parentheses. And then I'm going to go ahead and include my values. So this is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus on and on. So now I have e to the ix equals, let's talk about the value in blue. User, that will be for another day for sure. I'm just going to wrap this one up, and then we're going to be done for today, but maybe Friday. Friday is off trail, so we can definitely talk about other topics. If you guys recognize that first series in green, that is the Maclaurin series for cosine. So that is equivalent to cosine of x. Plus I, this is equivalent to sine. So this is going to be sine of x. How cool is that? Now, let's just go ahead and plug in pi for x. So we have e to the I pi equals cosine of pi plus I sine of pi. And let me make this just a tiny bit smaller, but hopefully you can see the values of this. So we have e to the I pi is equal to cosine of pi is equal to negative 1 plus I times sine of pi, that's just 0. So we have e to the I pi is equal to negative 1. Add the 1 to the other side. And voila, everyone. E to the I pi plus 1 is equal to 0. And that's Euler's identity. Pretty sick, huh? So all you have to do is have a solid understanding of Taylor series and Maclaurin series. And I guess you can say you need to have a solid understanding of how to take derivatives and a solid understanding of how to find trigonometric values at a specific point. And obviously recognizing patterns. But you are able to derive Euler's identity through the Taylor series of e to the x, and then just making sure you plug in this necessary values and just see those patterns and split them up. And that was it, everyone. This was really fun. I know we started with series, and we kind of kept it on the rails here because we talked about RRAM and LRAM and taking the limit as n approaches infinity. And then now we were here with Taylor series, aka Maclaurin series, and then we kind of did the Euler's identity at the end. Oh, nice. Good luck. Good luck. All they're going to tell you to do, especially for your test, I'm assuming, is just going to go ahead and take, 4 degrees or 4 terms of the Taylor series, and this is it. So all you have to do is make sure you show all your work whenever you're doing that on the test. All right, guys. So as I mentioned, I am recording this. It will be on my YouTube for you to watch later on if you'd like. Feel free to like the live. Follow me here on TikTok. Follow me on Instagram. Subscribe to my YouTube channel. I hope you guys have a great rest of your Thursday. I'm going to see you all hopefully on Friday. That's going to be off trail. So maybe some integrals, maybe some derivatives, maybe some volume. We'll see. Looking forward to that. Okay. So what level of math is this? This is technically Calc 2. Andy, don't worry. Just continue practicing your trig. We can definitely talk about trig later on, but everyone just seems to love the calculus, which makes sense. And Magic Mike, I'm trying to understand what you mentioned. Can you do the finding the derivative using the product rule? So you mean, for example, if I have f of x is equal to, let's just say, like x squared plus 1 times sine of x. Is that what you're referring to? Oh, don't worry. Honors pre-calc, you'll do great. This is great. Honestly, when it comes to math, seeing the material beforehand, you're going to see this next year. You're going to see the calc behind it. You can be like, oh my gosh, I saw this on TikTok, and that will be pretty amazing. So Magic Mike, if we're going to do the product rule here, just remember that the product rule is everyone writes it differently. So if it doesn't make sense to you, just, try to hopefully, again, just see different techniques. So the way it works typically, some people do u prime times v plus u v prime. Again, everyone has different notations. But the way it works is you got to separate this, or you got to identify the two functions that are being multiplied. And that's the x squared plus 1. Let's make that our u. And then our sine of x is v. Now, a lot of people do different charts for this, but I'm just going to kind of very quickly just explain how this works. So if we're going to take the derivative, applying the product rule, because we have two things being multiplied together, is we're going to follow this formula that I wrote in green. U prime times v plus u times v prime. And what that is the derivative of the first function. So we got to find the derivative of u. The derivative of u is the derivative of that x squared plus 1, and that's just 2x, times just the second function. We don't do anything to it. And now we're going to do plus the first function, which is our u, so 2x squared plus 1, times the derivative of the second function, which is going to be the derivative of sine, and that's just going to be cosine. So a couple of things that you have to keep in mind is, one, you have to remember how to take the derivative of trig values, how to take the derivative of other functions, and then obviously memorize the product rule. So if you look at it, this is just the sum of the two values, but you take the derivative of each of them separately. That's another way to think about it. And so now you just got to simplify. So for the first one, this just becomes 2x sine of x plus, if you wanted to, we can distribute that cosine to those two values. So this becomes x squared cosine of x plus cosine. But that is how you take the derivative using the product rule. One thing that I would suggest, Magic Mike, is go open up your book and try to practice as many problems as you can. Okay? Product rule is one of the most fundamental rules that you have to know, along with the quotient rule and the chain rule. So definitely just get cracking. Okay? The more practice you do, the better you're going to get. Anyway, so that was just a little extra lesson. You're welcome. I hope you guys, again, have a great Thursday. I'll see you guys tomorrow. Oh, wow, tomorrow is Friday. That's going to be fun. So tomorrow, maybe some Feynman technique. I'll try to see what I read tonight and then what I'm excited to talk about. So we'll do it then. Awesome. So tomorrow, 3 p.m., hope you guys are here. Until then, take it easy, everyone. Bye-bye.